Hello again. Up until now, we've been talking about Maclaurin series, which is a special type of power series. Now we're going to talk about another special type of power series called the Taylor series, which looks a lot like the Maclaurin series, but there are small differences. So let's look at the two of them and compare first. First of all, Maclaurin series are centered only at x equals 0. So I really don't have any room for expansion there. But with the Taylor series, I can center that series around any x value that I want. Let's call it x equals a. So what the Taylor series looks like now is instead of f of 0 and the first derivative of 0 and so on and all the derivatives at 0, now the function is being evaluated at a, the derivatives are being evaluated at a, and every x squared, x to the third has been replaced with x minus a squared, and x minus a to the third. All right, so that's how it's different. The approximations are similar too. I can approximate this by stopping the polynomial wherever I want and having an error term. And the error term still looks very similar to the Maclaurin error term. It's still the n plus first derivative evaluated at some constant c. It's still got n plus 1 factorial on the bottom, but instead of being x to the n plus 1, now it's x minus a to the n plus 1. And instead of the constant being between 0 and x, now it's between a and x. All right, so let's look at an example of this. We're going to find the Taylor series expansion for the natural log function at x equals 1. So the function is natural log of x. The first derivative is x to the negative 1. The second derivative is negative x to the negative 2. The third derivative is 2 factorial times x to the negative 3. The fourth derivative is negative 3 factorial times x to the negative 4. And then the fifth derivative is going to be 4 factorial times x to the negative 5. So if I plug in x equals 1, the function itself will be worth 0, the first derivative will be worth 1, the next derivative negative 1, the next derivative 2 factorial, and then negative 3 factorial, and then 4 factorial. So now I can write the Taylor expansion of this up to those terms, and I can keep it going using ... Just plugging in what I know for the function and derivative values. And if I simplify that, those ones I don't need to write, and I can write each term as just a simple fraction. You'll also know that some factorials got simplified. 2 factorial over 3 factorial leaves me with just a 3 in the denominator. 3 factorial over 4 factorial leaves me with just a 4 in the denominator, and 4 factorial over 5 factorial leaves me with just a 5 in the denominator, and so on. So with every term, I just end up with n in the denominator instead of any factorials at all. So the nth term is going to look like negative 1 to the n minus 1 times x minus 1 to the n all over just n. All right. Another example, if I wanted to use the 4th degree Taylor polynomial, which there it is at the bottom of the screen, if I wanted to use that to approximate this function, what's the maximum error that I would run into if x was somewhere between 0.5 and 1.5? So the error term is going to be the 5th derivative evaluated at c times x minus 1 to the 5 over 5 factorial. All right, and c is somewhere between 0.5 and 1.5. So that 5th derivative is 4 factorial times c to the negative 5 times x minus 1 to the 5 all over 5 factorial. And if I simplify that, I get x minus 1 to the 5 over 5 times c to the 5th. That c to the negative 5 got brought to the bottom, and it's now c to the 5th. So that has to be less than x minus 1 to the 5th over 5 times 0.5 to the 5. And once I simplify that and replace x with 1.5, then I will get 1/5 as my maximum error for the 4th degree Taylor polynomial approximating that function. All right, so that is Taylor series, a nice introduction to Taylor series. If you have any questions about this, please let me know, and I will see you tomorrow.